start the recording. Okay. Just get ready again. Right. So guys, we are starting with energy, which is topic 5. The next topic will be topic 7. We will not be doing topic 6. And then we'll be doing topic 7 and 8 afterwards. 7, 8, and 9. I'll just keep it like that for now. Yeah, then obviously there are other topics which we will touch on in part 2 and part 4. But we are all on page 121, and we'll be, for the next, I believe, 2 weeks, we'll be touching on this energy topic. Definitely it's coming in your next test. Yeah. So anyway, right. So before we begin, right, energy, I would probably like to share some other slides before I actually embark on this one. But we've all had ideas of what energy is, right? So for this lecture, we're going to develop our better understanding of what energy actually is and trying to quantify it, right? So energy is present in the universe in different forms, like mechanical energy, chemical, electromagnetic, thermal energy, nuclear energy, and even the inert mass contains a large amount of energy. I'm sure you guys heard of E equals m squared. So even mass has a high amount of energy. It's also important for energy. Energy can also be transformed from one kind to another. We'll talk about that. And, it's also important to know that energy is conserved, but we'll talk about these things. So there are different forms of energy, but what we're mostly focusing on is mechanical energy, which is essentially the sum of the kinetic energy, which we'll talk about. I know you guys are aware of this, and also the potential energy. So kinetic energy associated with motion, whereas potential energy is associated with position, or essentially gravitational potential energy. So what we're looking at is more the mechanical type. I did want to show some slides on all the different forms of energy. I might do that, but I think it's just get the crux of the work at hand, so we can get the ball rolling. I'll decide again whether it's important. Okay, so what we are looking at, getting straight to the point, let me just check my text here, textbook, is something called work. Right. So obviously we know what work is in normal language, but we obviously we're looking at mechanical work in this case. So what is mechanical work? So work has a different meaning in physics than it does in everyday usage. In physics, work is done only if an object is moved through some displacement. So for instance, you can imagine a box. You apply a force to the box, and as it gets displaced, therefore we call it doing work on an object. This could be deemed with a hoist. Hoist moving something up and down is an idea. A car moving, for instance, from one position to another. The engine will provide the force, which is the work. Obviously, a ship as well is another example. Yeah, so obviously a few examples. And I did say this is that doing work involves applying a force to an object while moving it at a given distance. I think we all can imagine that. And you might be tempted to think as work and by its definition, like force times distance, as you can see there, where F is the magnitude of the force and X is the displacement. But this only gives the magnitude of work done on an object where the force is constant and parallel to the displacement. So that, which must act along the line. I'm saying, okay, yeah, we'll get that. So this works for most certain cases, but generally there's a more proper definition for this. But anyway, so what we are looking at, so what this figure looks at is a block, a box, or a crate of beers, if you'd like. and it undergoes a change, undergoes a displacement along a straight line, and is subjected to a constant force. So that's important. We assume the force is constant and it's going in a straight line. The work done on the object by a constant force during a linear displacement, keyword linear, along the x-axis, also important, is given by the following equation over there, which is f of x times delta x, which is displacement, which is defined as xf minus xi, final minus initial. I'm giving you a slight hint here. You might have to work out various of these here using dimensional analysis. So I will include a bit of topic 1 in the next test, just to see if you know how to use a dimensional analysis. You make a note of that. That's important. Right. Notice that it's also one dimension. Obviously, delta x is a vector quantity. That means delta x could be positive or negative. However, what's important to note that work is a strictly scalar quantity. In fact, any energy transfers are also scalar. So you don't have to worry about too much direction, just the magnitude, which is essentially important over here. So I think that's all clear. Do you all understand what the definition of work is? Is there any questions before I move on? Any questions, guys? Or do you like hearing me talk? Any questions? Check who's here. Zizonke, Bonani, Tebo, Anton, Wendy. Any questions? Anthony, Nonlebo. Hello. Okay, cool. Guys, please engage. Do not be quiet online, you know. Right? Law is okay, thank you guys. The unit, as I was talking about dimensional, the unit for work is joules. I'm with joules, I'm sure of joules, which is essentially Newton meter over there, as you can see. Yeah, that's important. Guys, any questions, please either unmute your mic and engage or raise your hand. Okay, this is all the, I guess, all the preamble stuff before we actually get to where we need to be. Just give me a quick second. All right, yeah. So what is important over here? Let me go back a little bit. So I want us to talk about something here. Let me just go back. Okay, yeah. So we might have a force at a particular angle, which we all common of, which is a vector. And what is important here? So another definition of work is to relate the work done on an object to the angle of the displacement, or which with respect to the force, right? So take a look at that triangle over there. As you can see, it's a force at an angle. And obviously we have to take that force and split into its respective x and y components, right? However, what we have to notice is the following. Is that notice that the x component, which is parallel to the direction of motion, makes a non-zero contribution. So what I'm saying to you is we only consider the x direction in terms of the work. Because remember, at the end of the day, if the object was moving upwards, right, then we have to use a force in that corresponding direction, which is F sine. But in this case, which is moving flat across, we have to use F cos. I hope that's clear to everyone, right? So it's only when the force is going in a particular motion, that is when that's when it's contributing to work. If it's not moving that direction, it doesn't contribute to any work. So what it says is, notice that only the x component, which is parallel to the direction of motion, makes a non-zero contribution on the work. So non-zero meaning it contributes, not a zero contribution. Right. So I hope that's clear. And then again, the work done on an object by a constant force during a linear displacement is shown in this equation, which is basically the way d is the magnitude of the displacement and f theta is the angle, and which is the which makes obviously the angle between the vector and the change in x. I hope that's clear to everyone. Do you all get that? Is that clear? I want 3 thumbs up before I proceed. We're nearly going to do an example. We're getting there. Is that clear? Luckily, the lecture is recorded, so you guys are sorted essentially. But yeah, I'd like to know if you guys get it. Yes, okay. Very important example because I will test your understanding. Okay, thank you. I appreciate that, my students. So moving on. Okay, still more. So let's look at another case, right? So we can use our definition for work when the displacement is not specifically along the x-axis or another another case. So in this figure, right, who can we use? Miss Melina is carrying a bucket of water, right? And she's carrying a bucket of water horizontally at a constant velocity. I think that's, we can imagine you're basically walking with a bucket of water. However, there is an upward force exerted by the man's hand on the bucket, right, which is perpendicular to the motion, right? We're all aware of that. And however, that force does no work on the bucket. I don't know if that makes sense to everyone, right? This can also be seen from the equation over there. Essentially, what this means, if you look there, is that the upward force exerted by Miss Melina's hand on the bucket is perpendicular of the motion and does no work on the button. So you look at the equation there, and this is because the angle between the change in x and the f is basically 90 degrees. And if you type in cos 90 in your calculator, or if you know your cos graph, it will give you 0. So therefore, in the same breath, in the same way, the force of gravity also does no work. So any force perpendicular, because it's cos 90 basically, is exactly perpendicular to change in x or direction of motion, it's therefore 0. So that's quite interesting. Even though she's, even though she's holding the bucket and the force is acting on it, that force is at 90 degrees and cos 180 as well. I believe it's 0 if I'm correct. Is cos 180 0? I think it is. And therefore, that's the reason why it's 0. It's just not simply 0. Mathematically, it's telling you why. I hope that was clear to everyone. All right. This one. Yeah. So again, work can be either positive or negative. That's important to note. And in our definition of work, which is F and D, both of those is typically are not negative. That means work is positive or negative, depending on cos theta is positive or negative. So obviously, cos theta can be negative or positive depending on the angle. So this also depends on the direction of the force relative to the direction of the displacement. So when these vectors are pointing in the same direction, for instance, the change in x over there, we'll talk about that now. We find out that in this case, cos will be 0. If we have cos 0 is 1, positive 1, then the work is positive. So work can be positive and negative, it's not more of a directional kind of thing. So they give a quick example over here. So they say Stanton, for instance, is lifting a box, shown in that figure. And the work he does on the box is positive because the force he exerts on the box, right, is upward, and that's in the same direction as the displacement, right? That makes sense. However, when Stanton lowers the box in this case, the motion of the box is downward. But then now, if you think of that, that'll be cos 180 degrees, and therefore if you say cos 180, cos 180 is equal to -1, and therefore the work done by Stanton is negative, right? So it is important that we still have positive work and negative work. It's there, even though it's still a scalar. But in general, when part of F parallel to displacement works in the same direction, it's basically positive, and if it works in the other direction, then it's going to be negative. So that's all clear. There are some quick things to talk about, but for now, we can officially start on our first example and exercise, right? So let me just prepare the whiteboard. Guys, is there any questions? Or you guys have PhDs in physics, so you guys are good. You guys have done this in matric, in high school, right? Am I correct? Let's quickly see here. Any questions, guys? Can I move on? Are you ready to solve your first problem? Here's the whiteboard. Okay, so we are solving. That's on page 1 to 4, example 5.1. Okay. Just get the textbook quickly ready. Just give me a second. All right, guys, can you all see this? Can you guys all see this? Cool. So let me just zoom in for you a bit. Obviously, you have the textbook on hand. Yeah. So I'm just applying the basic definition of work over here. And let's see what we can cook up. Okay. So we have a man returning from a successful fish icing trip, ice fishing trip. I don't know who does that. And he's basically pulling a sled full of salmon. Right, so we've got fish over there, and he's pulling it. They're saying the total mass of the sled and the salmon is around 50 kilograms, and he exerts a force of 1.20 times 10 to the power 2 newtons on the sled by pulling the rope. Right. A, how much work does he do on the sled if the rope is horizontal to the ground? All right, that's the first thing. So theta is 0. And he pulls it for 5 meters. B, how much does he do at 60 degrees if he pulls the same distance? And then C, at a coordinate position of 12.4, the man lets up the applied force. And then a friction force of 45 newtons between the ice and the sled, bring the sled to rest at a coordinate position of 18.2. So obviously they're just talking about the change in distance there. How much work does friction do on the sled, right? So again, we all have to apply our basic values. So you guys have the formula sheet um, for this for the subject, and obviously, yeah. So we know our basic definition. I'll just write it for you there, and we can begin. Does the question seem easy, guys? You guys understand what must be done before I embark? I see word changed again. The whiteboard. See, cool. Okay, let's. Thank you. I'm not sure it's Mr. Mulaturi. Forgive me. Okay, just get my graphics tablet in. Doing any sound? Let's see what it writes. Guess like it's working. Thank you. All right. Let's get go. Let's get moving. So just keep the yellow in. Let's lock in. Yeah. Okay. So A, we know the work equals force times this. And what's important for the first condition is pulling at an angle of 0, right? So obviously we can further stress this definition is F cos theta. We do not consider F sine theta because it's not in the direction of motion. And surely you'll be tested on that. That's all I'm saying. All right, so we have 1.2 times 10 to the power 2, which I believe is 120, if I'm correct. Cos of 0, I think cos of 0 is going to be 1. And in this case, he's pulling it for 5 meters, I believe. Right? I'd like you guys to give me the answer. You guys can calculate it for me. That's why you're here. I hope you guys can all see this. You might ask why this is important. Maybe if you're designing a machine, if you ever do, you can exactly figure out how much energy you require to pull a certain weight. Obviously, sizing the motor or maybe pump. There's many things you can actually use these equations for. All right, let's see how much work is done. Is that Wendy? No, it's not. Is it, I think that's Naledi, I'm not sure. That's 600, right? 600 joules. Are you all content with this? So look at the book again. We all get 600 joules. Cool, perfect. So the next one, quite easy as well. The very basic stuff. Work, F cos theta. And in this case, changing X. So now it pulls at the same distance, but now at 30 degrees. So obviously you guys can sort that out. So I'll say 1.2 times 10 to the power 2 cos 30 times 5. Right? How many joules is that? Let's see what you get. quickly see. Uh, 12.62 joules, fantastic. So looking at this, my beloved students, you might ask, so why is this important? Or, what's this about? Look at this. If you were to pull something, right, and this is obviously I'm imagining you're pulling a bed, or you have a bed, right, you're moving a bed. And if you pull the bed horizontally, you require a lot more energy if you were actually to lift up the bed and pull it. Does it make sense to everyone? And can everyone picture that? If you have the bed and you drag the bed across the floor, for instance, you require a certain amount of energy. But if you lift the bed up on its two legs and you pull it up a bit at a particular angle, it moves a bit more easier. Does it make sense to everyone? Wendy, Lucizo, Mr. Mzulu, Singalaka, Mr. Nina. That's the idea here, right? I want you to quickly check for me. At angle, do for me 45, 60, and 75, right? I think I'm thinking the right thing. So let's just quickly check how much work done at 45 degrees. Let's do it 60 and then it's 75. Just a quick check how many joules required for each one. Can you guys just quickly give me that answers? So when you're interpreting these values, I want you to always imagine, that's the idea. What will require the least amount of energy? Hey, fast. That's 424, right? I'm going to call it 424. Not going to be too fancy there. So even less. Obviously, it doesn't mean you must take that particular angle. It has to be practical. I mean, if you can't lift something to 60 degrees, then it's not possible. But I think that's the interpretation. Even 300 joules, so even less energy, literally half the amount of energy, if you have it at 60 degrees, which is a bit difficult to get up, depending. And then 75. 155, even less, right? So that's just the indication. And I think I must stress not necessarily that the higher angle you go, that obviously it'll be less, but sometimes it's not practical. You can't maybe legit lift the bed up 90 degrees. It might require more energy to lift upward. But in the case of moving it horizontally, it might be better. I think that's the what you're looking at. Nevertheless, just a quick one. And so at C, the Leica coordinate position of 12.4, at a coordinate 12.4, the man lets up the applied force. So what I'm saying is that he pulls it and he lets go. So obviously now the sled starts to move across the ice and then eventually ends off at 18.2 meters. So obviously you have to subtract that too. And essentially the frictional force essentially lets the slide stop. So in this case, we apply the same idea of thinking, but they just call it fancy the work of friction. So typically you want to denote work on friction as a separate thing. So it'll be F of X times delta X. And what's important to note, friction, right? What we do here is we call it negative because obviously we assume that light is positive. So I think we're all aware of that. And then obviously we are timesing by the change in distance. In this case, it'll be the 18.2 minus the 12.4. And again, you'll see the negative work here. So that's what you need to do, right? So just give me the answer, then you're on your own for the exercise. Yeah, I think our units are all right. quite easy for now. Yeah, it's gonna get a bit more fun. All right, what do we get? Minus 261. I'm content with that. Thank you very much. Okay, so that's quite easy to understand. Some nice, easy marks here. So just to understand your comprehension, it's always good to do exercise. So I'll give you guys 10 minutes, I think, 5 to 10 minutes, um, to quickly do this one. If you guys are struggling, I'll probably do it with you. So just always make sure you do the exercise here, right? And then we can move on. Okay. You guys will see that. Obviously, it's in the textbook. So, oh, Lucizo, get your pictures at least. So you are. It comes over here. So it says the coordinate position of 18.2 meters. You got it, Lucizo? What's in the question? Guys, I'm always assuming you have the textbook next to you. Just by the way, that is my assumption. Cool, okay. All right, there you go. All right, guys, time's up. You guys have any problem with it? 8 meters, fantastic. You got the answer, great work. Nomzebo, excuse me. Are you guys good with it? Wendy, Lucizo, Colin, Stanton. You guys get A and B. It's just for comprehension's sake to see that you've understood. Fantastic. Guys, always practice while you are here. It's you're preparing for you're doing your homework, you're studying, and at the same time you're practicing for your assessments. Miss Mina Singalaka. Kuhle, did you get it? Penny, Tefo. Okay. All right, guys. I think that's more than enough. Thank you very much. Okay, so let me just continue with the lecture. We can do one more. Okay, cannot one of those, but yeah, anyway. Let me just share the slides again, and then just get back into the problem. Just give me a second. I'd like to share it. Okay, second. Where is it? Okay, right. And you guys can see it. Hello. Okay, there you go. Took a bit of time for some reason. All right, there we go. So we're going to talk about work and dissipative forces. Yeah. So what this essentially is, just talking, just elaborating or elucidating on the concept of frictional work, right? So frictional work is extremely important in everyday life, because doing almost any other kind of work is impossible without it, right? Cars wouldn't work without friction. For instance, tires, the tires on the ground, there's friction over there. That is why your threads in the tire it's there's grooves on it to create more friction. Brake pads, for instance, to stop any braking system, it has an element of friction. Um, Gearing, for instance, as well. Anything touching each other, that's where there's going to be friction, right? They also talk about conveyor belts, yes, or even our muscle tissue, right? And what they say here is friction is a complex process, and it is caused by numerous microscopic interactions over the entire area of the surfaces in contact. So what you can just quickly imagine there is a metal block sliding over a metal surface, right? And if you look at this microscopic teeth in the block, which obviously you have to look, you can't actually see it there. You have to look at the microscopic level. And microscopic teeth in the block encounter equally microscopic irregularities in the underlying surface. So obviously, look at that surface there, you'd see all these grooves. Likewise with that thing over there. And if you look at there, if you look at a razor blade, for instance, it seems smooth, but if you actually look at the edges, right, of the microblade, it will show you several of those irregularities over there at figure B. So you can imagine when a metal block slides over the surface, these irregularities pressing against one another, they deform, they'll change in dimension, they get hot and wild to opposite the surface. So those interactions, obviously, there's an interaction between the two touch. And where this comes into the work is that work must be done in breaking those temporary bonds, which comes at the expense of energy of motion of the block. And that's what we aim to discuss in the next few minutes. And the energy lost as the block goes, the energy lost is by the block that goes into heating, by the block and its environment. So as it's rubbing each other, and obviously we've seen rubbing two things, and even in two hands as you rub it, right, as I'm literally rubbing it now, you can feel heat, and that is caused by the friction between the two stuff, right? And the friction force of the two objects in contact, in this case the metal surfaces, and the relative motion to each other always dissipates energy in these relatively complex ways. So for our purposes, the phrase work done by friction will denote the effect of this process on mechanical energy alone. So I mean, long story short, the frictional force also produces work, but in this case, it'll be negative. Yeah, it's. I mean, we've kind of seen it in the previous example, but obviously I'm just bringing it more. But sometimes we have these problems, and we have the normal force, the force applied, and then the frictional force. And when we finding out the total work done, we're going to have to subtract, the work done by friction, because obviously it acts in the opposite direction, but at the same time it impedes the motion. So that's essentially what it is, and we walk on to the next example. So that'll be the next section. So I'll just share my whiteboard again with you, and we can do example 4. What is this again? Example 5.2. All right, nothing too crazy. We probably might do 2, and then we can call it a day. Then I'll see you tomorrow morning again. Okay, so let me just open the whiteboard for you. Again, we're on page 125. Okay. Guys, I urge you again, please complete this feedback for me. I didn't check. Excuse me. Okay, I'm just going to paste this again. Share my whiteboard. So it's going to be easy now, but we're going to pick up a bit over as time. And yeah, we have, let me just count counting this topic, 2, 3, 4, maybe 5, 6, 7, 8. We have 8 topics to do in this next upcoming weeks. I'll say 6 to 8 topics here. So I'm just making you aware. You're in for a nice ride. All right. Same question. Okay. Excuse me, just got a bit of wind. The question states, calculate the work done by friction when an object is acted on by applied force. So suppose that in example 5.1, the coefficient of the kinetic friction between the loaded 50 kilogram sled and snow 0.2. And then A, what I ask you, the man again pulls the sled for 5 meters, exerting a force of 120 newtons at an angle of 0. Find the work done on the sled by friction and the net work. Repeat the calculation if the force exerted at 30 degrees, right? So it's the same, but now they want the work done by friction on its own, right? Is it in totality on its own? So I'm quite confused. Let me just have a look at what the book says. I'm sure it could be in totality. So let's have a look. Yeah, I guess it's all together. Right, so we have the sled. Not gonna make a long story. Okay. Change my pen color. I'm assuming you can see. That's 30 degrees over here. Oh, no, that's 0 in the first case. And we've got our FK. Okay. So again at 5 meters, not gonna, you get the idea. Starts at 0 and moves 5 meters, so it's 5 meters. So I can't see the screen. So just refresh on your end. Who else can't see? Anyone else can't see? Just let me know. Okay, can everyone else see? Stanton, Zizonke, Winnie, can you guys see? Nande? And guys, please, please tell your colleagues I'm taking attendance, and I'll be telling the HOD not attending. I have a textbook, so okay, cool, no stress. All right, so let's compute the work done by friction. What is the definition of friction? It's a function of two variables. Ms. Anthony, can you please tell me? She is online. Mr. Tefo. So Mananga. Matata, sorry. What is my friction equal to? Guys, I'm waiting for the formula for friction before I move on. No, not that definition, man. The one with mu. Yes, mu k times n. Thank you very much. Okay, so in this case, we need to find obviously the normal force of this particular thing, but we do know that the normal force and the weight doesn't contribute to the work done because it's not moving in that direction, right? So, but we obviously need the normal force, so therefore we sum up the forces in the y direction, make that equal to 0, and we know that the normal force is going up minus the weight, that equals 0, and therefore the normal force equals mg, right? So we contend to that, and then we do this, we check the force in the x direction, obviously. You know, it's for the work. I don't have to be this fancy really. So we can just go, let's go straight to the point. Work equals force, or F net, times change in x. In this case, it's 120, right? But now, as I said, before I do that, I said define the work done on the sled by friction and then the net work. Okay, they did say that. So let's find the frictional work. So work frictional will be the frictional force times change in x. So in that case, at 0.2. The normal force is mg, so that's the 50 times 9.8 for you. And then it moved for 5 meters. So someone can please give me how much work is done by friction, or how much work is essentially taken away by friction. 490. I want to see negative 490. Right? Are we all content with that? It's negative because it's acting in the opposite direction of motion. Yes. Well, is that not lady? I keep on forgetting. It is not lady, right? Yeah. Sorry, man. I keep on. Forgive me. That is what I'm looking for. And obviously, we want the network. So we're just going to go here. Network is Fnet times change in X. And we know that's 120. Wasn't no. Oh, we still have to work out the. Can we just do this? Can we say 120 minus 0.2 times 50 times 9.8, right? That's that force minus that force, brackets, times by 5. I think we can do that. And we should get the network. And obviously, the answer should be in joules. So what's my network? Is that correct? Yep, I'm happy with that. 110 joules. Can you see, if you look at the previous example, I'm not sure it's on the same one. It's not on the same thing. Yeah. How little energy. I mean, it's so little now. Do we all agree with that one? Do we all agree with that one? Fantastic. Okay. Thank you, Nadidi. All right. So next part, I like you guys to try quickly. Seeing you guys have experience. And now we're going at 30 degrees, right? That's 30 degrees. If we still set the same value of 120 newtons, and our frictional force, let me work it out for you. It's my actual calculator. 0.2 times 50. No, I can't. Fk. You have mg and your normal force. So the first step, as I mentioned to you in class last week, Thursday, you're going to have to sum up the forces in the y direction, right? You want to get the normal force again, but obviously there's a spin because it's at an angle. I like this question. All right, so the first step is get the normal force in terms of all the other variables. I'll give you guys 5 minutes for that. So is it all clear what you need to do next? Is it all clear? Naledi, Singalaka, Rilo, whatever that is, Stanton. Please tell me if I'm able to get the next part. Okay, N is 60. How did we get that? Are you sure about that? Anyone else agree with that? I'm not sure myself. Let me just quickly check. Definitely not. Definitely not 60. I'll give you guys 2 more minutes. It's not joules, you're just finding a force, Singalaka. So change your unit. 430 watt, guys. I don't talk only magnitude. Newtons, 430 newtons. That is correct. If you got that, you're definitely on the right track. All right. So the first thing you want to do, Mr. Tefo, is see all the forces. Obviously, you want to split these components quickly. Let's just choose this. We're going to have our F cos over here, all right? And we're going to have our F sine over here, right? Okay, so we look at the forces up and then the forces down. We have the normal force going up plus F sine 30, and we minus mg, which is the weight. Okay, so therefore now I have to carry everything over to the other side. Then we're going to have mg minus F sine 30. And of course, we have to populate this. That's 50 times 9,8 minus 120 sine 30. And if you do that, you should get 430 newtons, right? Obviously, the work done by friction in this case is how much will it be, more or less at 0.2. We can always keep the negative sign there. We times the 430, and obviously we must times it by 5 as well. And if you do that, you should get an answer of, let me have a look here. I believe, go to the book over here, get 4, oh, is it also 430? So all 430, I guess. I did not add the mg. Yeah, exactly. It's all minus 430, I believe. Yeah, minus 430 joules. Okay, apparently this is minus 430 as well. Let me just confirm this. Yeah, no, for sure, it's all 430. And then the network, same as before. But obviously, you can just go 120. But obviously, at the time, got all of this now. So it's going to be 0.2 times the 430, which is at the mu n. And we can just times it by 5. Okay. And what I like they did there, something very important, on the work net, they took the work applied, which is due to the force, right? The work of friction, right? And they put the work of the normal force plus the work of gravity. And we know that these guys are 0 because they are perpendicular, right? They're not contributing to, they're not in line, they're not, they're perpendicular to the motion, and they're not contributing anything. In fact, they are cos 0 and cos 180 or 270. So they cos 90 and cos 270. So therefore 0. Is that all clear? So what's my network? What is my network? Waiting on you guys. $170. Fantastic. All right. Do we all get this? All right, guys. 86.2 now, lady. How did you get that? That's the answer in the book here. According to them, you should get 9 joules or 90 joules. Did I make a mistake somewhere there? 120. Is my coefficient right? There's a coefficient there again. 0.2, right? To be, yeah, I also get 170. What did I miss there? Oh, I see. Remember, I didn't. Yeah, it's at an angle. Thank you. There we go. So I gotta fix this up. Cause it's an angle. So this is cos 30 minus the what is this guy again? 0.2 times 430. There we go. Hey. And you should get, hey, prof na lady there. 89.62 joules. Yep, it must be the positive, sorry. 90 joules. All right, so we've reached the end of today's session. But for homework, it's an absolute must. So immediately after the session, do exercise 5.2. It's on the same thing. And I prescribe you to do 3 more examples. Right? Or exercises, sorry. The back of the book, the back of the chapter, sorry. Very important chapter, guys. So ensure you're doing it. Yeah, there's some good examples you can do there. Yeah, you can have a look there. Number 6, number 5, number 4, number 7, number 8. Nice, simple examples. All right, guys, are there any questions before I close today's lecture? Tomorrow, I will see you online again. I will post the announcement. But is there any questions? Before I close today's lecture. Any questions, guys? Stanton, Wendy, Zonke, Ms. Marina, Okushe, Latudi. Are we all content? No questions. Guys, please engage before I close. All right, guys. See you tomorrow morning. Thank you very much, Nusizo. Guys, do the exercise and then do the 3 more exercises. That's your prescription for today. And tomorrow I'll see you in the morning. Okay, guys? Have a good day further. Cheers.